In this presentation, we examine different types of forces that we might see in nature, and then eventually we will apply these types of forces to different types of problems. So the first type of force that we're all familiar with, but we probably don't even realize it, is something called the support force. It's also called the normal force, and it's a force that's exerted when two objects are in contact with one another. And the two objects that are in contact each exert forces on one another. So the first thing is the force, the normal force, is always directed perpendicular to the area of contact between two surfaces. And the harder that the two surfaces push together, the greater the normal force is. So here I have a picture of a person. Let's say that that person has a weight of 100 pounds. And they are standing equally on two scales down here. So their body is exerting a force on each one of these scales. And because they are standing and their weight is distributed evenly between the scales, if they weighed 100 pounds, then each scale would read 50 pounds. Now in this particular case, you can tell that the person has shifted their weight over to the right-hand scale more so than the left, and they weigh 100 pounds, but the scale on the right is going to weigh a greater amount than the scale on the left because the person is pushing harder on this surface. There's a greater normal force. In order to further examine normal force, we could think about a block that is released from rest, and we can think about what forces are acting on it. So here I have a block. Suppose I pulled it above the ground and I let it go. Once I let it go, the only force that's acting on it is the force of gravity. There's nothing holding it up, there's no hand, and there's no air resistance. So this block would actually accelerate under the influence of gravity. Now eventually this block is going to hit a surface and it's going to stop moving. So imagine I had it above a table and it eventually hit the table and then it stopped. Now the block is at rest, and if it's at rest, it has zero acceleration. If it has zero acceleration, that means that the net force that's acting on that block has to be zero. So that implies that there has to be a force acting on this block because it's in contact with the table, and that force is what we call the contact force or the support force, or more specifically the normal force. So the normal force is always going to be directed perpendicular to the area of contact. So here's my area of contact between the block and the table, and that force is directed opposite it. Now, in this particular picture, the normal force is exactly equal to the weight of the block. Because there is zero acceleration, the net force has to be zero, so the upward force is going to have to be exactly equal to the downward force so that they can cancel each other out for a net force of zero. So the normal force is always going to be something that occurs when two surfaces are in contact. Now just a quick note, sometimes I will write the normal force as F with a subscript N, and sometimes it's written as just a capital N. When you use capital N to represent normal force, it can be confusing because you can think of it as newtons, so I've written it here as F with a subscript capital N for the normal force. So one of the things that we could ask is, how does a scale actually work? Well, the scale measures how hard two surfaces push together. So in this case, the block is sitting on the scale, it's pushing on the scale. It turns out the scale is pushing back and holding the block up with a value that's equal to the normal force. So this block has a weight of 10 newtons, and so there's also a contact force holding it up that has to be equal to the weight of the block. Now the scale is actually going to read whatever that contact force is of how hard the block is pushing on the scale, and in turn how hard the scale is pushing back and holding up the block. So in this example, the scale always reads whatever that contact force is or that normal force. Well, I don't know if you've ever done this, but if you've ever been near somebody who's on a scale and you try to trick them, you can go over and you can put your foot down on the scale, or you can push on them, and you can cause the scale to read a bigger value. So suppose that we have that same block on the scale, but then somebody's hand comes over and pushes on the top of the block. Well, in this case, there's going to be a greater contact force because not only is the block's weight pulling it down, but now the hand is also pushing down. So you've got two downward forces, 10 newtons and 10 newtons. And if this system is in equilibrium so that the sum of the forces have to be 0, then there has to be an upward force to cancel out the two downward forces, and that normal force is now 20. Now the scale is actually going to read a larger value this time. It's going to read that contact force of 20 newtons, and it's reading a greater value because now the surfaces are pushing together by a greater amount. I think I've sort of already, answered this question earlier, but I have a person who weighs 150 newtons. They step evenly on two bathroom scales. We can say that essentially, the left foot scale reading and the right foot scale reading are both going to read, sorry, wrong one, are both going to read 75 newtons. So basically the scales read half of the person's weight because they're evenly distributed between the two scales. Now, if the person leans to the right over here, then the scale on the right is actually going to have a larger reading. So the right foot scale over here, or the right hand scale, is going to read greater than the other scale. Now, this is deceiving the way I have it worded, so I guess I have to be a little bit careful of whether it's right foot or left foot and what you're thinking about it. But the scale over here on the right, which I guess is the left foot, would read a larger value than the right foot scale or the left hand scale. Sorry for the confusion. The wording of this question is a little bit deceiving. But the scale over here is going to read a larger value. Another type of force that we may encounter is something called friction. And I've really sort of, in previous lectures, we've sort of talked a little bit about the fact that there could be friction. But friction occurs when two surfaces rub together, and even if the surfaces appear to be smooth, they really are rough on the microscopic level. So here's two blocks, and they might seem, it could be like glass, and they could seem very smooth. But if you look at it microscopically, there's little bumps on those surfaces, and so when they rub, those bumps exert forces on one another. The frictional force on an object is always directed opposite the motion, or opposite the way that the object is going to tend to move. And so it never helps the motion, it's always hindering the motion in some way. The amount of friction on a surface or on an object depends on what the material is made of and how they're rubbing together. So if you took a piece of rubber and you tried to rub it on a surface of concrete, that's going to have a different impact than, let's say, taking a bar of soap and rubbing it across a piece of a concrete surface, right? So the amount of friction between two surfaces depends on the materials that are actually rubbing together. And the way that we determine, the type of material is by something called the coefficient of friction, and we'll see how that's used in a little bit. But the coefficient of friction will tell you the type of surfaces that are rubbing together. The other thing that the friction depends on is how hard the surfaces push together. So the greater that the force is between those two surfaces pushing together, the greater the amount of friction that you're going to have. So a good example of this is if, and I can't do this visually, but if you were to take your hands and you were to put them together, and then you would rub your hands together where you're not pushing very hard, you can experience a little bit of heat. But if you push the surfaces together really hard, your two hands together really hard, and then you rub, you're going to get a whole lot more heat, which means that there's more friction. So the frictional force depends on what are the materials made of that are rubbing together, and how hard are they pushing together. And how hard they're pushing together is basically the normal force. So we can write an expression for the amount of friction on a surface, and we write friction as a lowercase f, and we can say that the frictional force is directly proportional to the contact force, the normal force, and it also depends on this coefficient of friction, which is the type of surfaces that are rubbing together. So there's two different types of friction. There's something called static friction and kinetic friction. Static friction occurs when the two objects are in contact with one another and a force is applied on the object, but there's actually no motion between the objects. So you can imagine that you're at your house and you have to move the couch across the room. You push on the couch, but it doesn't move. So you're applying a force. It's not moving. The sum of the forces have to be zero, so there has to be something resisting the motion when you push it in one direction. And that's static friction because the couch doesn't actually physically move when you push on it. Now, when you push on an object and it does move across a surface, then kinetic friction takes over because the surfaces are moving with respect to one another. In general, the amount of static friction between two surfaces is greater than the amount of kinetic friction. And the easiest example, again, I can think about that is it's harder to get an object in motion versus keeping it in motion at a constant speed. So again, back to the couch. That couch was really heavy and you're trying to move it across the floor, and it was really hard to get it going, but once you get it going, you want to keep it going because it's going to be easier to keep it moving versus stopping again and starting. So I have this table over here, and this table is representing different types of surfaces rubbing together. So I have steel rubbing against steel, aluminum versus steel, wood on wood, glass on glass, ice on ice, lots of different surfaces rubbing together all the way down to our joints in the human body. So you'll notice that depending on the type of surface, you have different coefficients of friction. So the second column, I guess, is the coefficient of static friction for different surfaces. So we can see that the surface that has the greatest amount of static friction is rubber on concrete. That should kind of make sense because our tires are made of rubber and our streets are often made of concrete. So that has a lot of static friction associated with it. You park your car on a hill, it doesn't start to slide down the hill because of the static friction that's there. So large coefficient of static friction means that you're going to have a larger frictional force between surfaces. It's going to be harder to get them moving. So the easiest thing to move here, of course, is our joints. We don't want to have very much static friction in our joints. We want to be able to move them very freely. And then next to that is ice on ice. Ice does not have very much friction at all. On the other hand, once an object is in motion, it has kinetic friction take over, and so we have coefficients of kinetic friction here. And we can see that if we look at any surface, the coefficient of kinetic friction is always less than the static friction because it's easier to keep an object in motion versus starting it in motion. So those coefficients of kinetic friction in general are always going to be less for a given material as I go down. Right? So I get down to ice, static is 0.1, and then kinetic is 0.03. So the coefficients of friction are going to tell you something about how easy it is to get an object moving, how hard it is to get it moving, and then also to keep it moving versus at a constant speed. So the frictional force is going to depend on these values, these coefficients of friction, as well as how hard the surface is pushed together. So let's try to examine these coefficients of friction and see if we can understand what's going on. So I have identical objects. They have the same mass and size, and they're placed on surfaces. So when I say the same size, that means that the surface area that's in contact with the ground is the same size. And which object will be the most difficult to start in motion? So if I had a steel object placed on steel, if I had an aluminum object placed on steel, copper on steel, and so on, which one of these would be the hardest to actually start moving? So in order to determine that, I have to look at the coefficient of static friction because I want to start it in motion, and so I have to overcome that static friction in order to do that. So whichever of these objects has the largest coefficient of static friction, it's going to be the most difficult to start in motion. And when I look at the static frictional force, glass on glass has the largest coefficient. That would be the hardest to start in motion. I could ask the same question, which object will be the most difficult to keep moving at a constant speed? So I want to keep it going, it's in motion, So I need to look at the coefficient of kinetic friction because that describes the object in motion, and which one of these has the largest coefficient of kinetic friction. That would be the most difficult, would have the largest frictional force, be the hardest to keep in motion, and in this case it would be the steel on steel that has the largest coefficient of kinetic friction. The other type of force that we may encounter is something called tension. And tension is basically a force that is distributed through a rope or a cord or even a chain for that matter. So we go back to that example that we had before. So we have this block, and if I released it, it would accelerate downward due to gravity. The only force that's acting on it is the force of gravity. So what if I took that block and I attached a cord to it? And the block just hangs there. So it's not accelerating. The sum of the forces have to be equal to 0 because the acceleration is 0. It's at rest. And so there has to be some force that's holding this block up. And that force is the tension which acts through this cord. So anytime there's a cord attached to an object, there's a tension that acts along the direction of the cord and at the area of contact between the cord and the actual object. So we call that the tension. Now in this particular picture, this force would have to exactly equal the force of gravity because this system is not moving, it's just sitting there. But this tells us that cords and ropes and chains also can exert forces on objects, and that force is basically just because of the particles that are inside that rope are exerting forces on one another, which translate to the force on the object itself. So similar to the contact force or the normal force, we can have a situation where, like here, this person is hanging from gymnastic rings, and suppose this person had a weight of 100 pounds again. Similar to the scales, they're holding on to two cords. So their weight has to be distributed between those two cords evenly. So each of these cords would have a tension of half of the weight, which would be 50 newtons apiece. So if she had another cord like attached in here somewhere, like a third cord that was like attached around her waist or something that was holding her up evenly, then her weight would have to be distributed between all three of those cords. This is again similar to the person on the scale, where the individual seems to be holding on tighter to the left hand cord and kind of releasing over here. So in this case, the left hand cord would have more of the weight and the right hand cord would have less. I mean, eventually if she let go of that, all of her weight would be in just one cord. If you have a pulley system or a cord that goes over top of a, in this case it's a pulley, and you hold on to each side, this is the same picture. Essentially, if I cut this off, this picture is exactly the same as the individual that's holding on to the two rings. Each side of this rope would have to get half of the person's weight. So the tension in this cord essentially would be half of that person's weight. So when you're thinking about things like that, a cord going over a pulley has to have the same tension throughout the whole string, cord, and so on. So you have to think about what's connected to the cord.